Welcome. Thank you for joining us today for a panel discussion about the benefits of high albedo surfaces like cool roofs, solar reflective walls, and cool pavement, which reflects sunlight back into space and help curb the greenhouse effect. My name is Jonathan Parfrey. I'm the executive director of Climate Resolve. For more than a decade, our nonprofit organization has advocated for solutions to extreme heat and the urban heat island effect. We've led efforts to get the aggressive cool roof building codes passed in a major metropolitan area, starting with the city of Los Angeles, continuing with Los Angeles County. And we've been a partner with Streets LA in deploying cool pavement pilot projects throughout the city. This summer, we're working with a great company, GAF, to implement a 10 square block cool pavement project in the neighborhood of Pacoima. And today, you'll be hearing from four of the world's leading technical experts on solar reflection and their benefits. And given today's ruling by the Supreme Court, there is an added urgency to this information. Cool surfaces produce multiple benefits. Cool surfaces can protect public health. Cool surfaces can also reduce the generation of smog. They can reduce energy use, saving customers money. Cool surfaces can help the electric grid become more resilient. And as you'll soon hear, high albedo surfaces reflect the sun's energy, reducing the greenhouse effect that is behind climate change. The Earth's natural albedo used to be about 0.3 SR, but in our cities, it's now about 0.1 SR. So higher albedo cool surfaces would help return us to an albedo that is much more in line with the historic averages and would undeniably help us in restoring the Earth's energy balance. And this is why Climate Resolve is hosting this webinar. We really need to attract public attention and private capital to high albedo solutions. We're especially desirous to promote projects that benefit low-income communities that cannot afford to fund development of cool surfaces at scale. And speaking of funding, I'd like to thank our sponsors for supporting this event: Climeco, Skanska, Latham & Watkins, GAF, and the Adrian Arsh Rockefeller Foundation Resilience Center. We couldn't have hosted this free event for all of you without their support. And with that, I'd like to introduce you to Climate Resolve's Deputy Director, Bryn Lindblad. Bryn is a leader in cool surfaces, particularly with cool streets, and she's helped our organization lead an effort to win a substantial grant for the city of LA to implement cool streets in the San Fernando Valley. This effort will create a cooler, more livable neighborhood for people to bike and walk and use local transit. Bryn.
Thanks, Jonathan. Hi there. Try to give a warm welcome to our folks who are tuning in from across the world this morning, afternoon, evening, depending where you are. I'm Bryn Lindblad, Deputy Director of Climate Resolve, and I welcome you to our Reflecting Sunlight webinar and networking event. Climate Resolve's theory of change has to do with making local solutions to climate change so practical and multi-benefit that they're simply irresistible. I'll refrain from being my normal advocate self for a minute here, though. Today's panel is a scientific, technical one. I invite you to come to your own conclusions and relish this opportunity to hear from and discuss the potential benefits of high albedo surfaces with some of the world's leading experts on radiative forcing. Before we get to the science, though, just a few more words about application. Reflective surface solutions are available today. They're already being manufactured and deployed in the form of cool roof shingles, reflective coatings on flat roofs, cool paints on walls, and cool pavement on streets, such as that which you see behind me. However, this is not yet the norm everywhere that it could and should be. Technology is available and the science is clear. we now aspire to get the policies and institutional to catch up. Our goal is for policymakers and other stakeholders to take note of the climate change mitigation benefits that get discussed today, and to accept an open invitation from us to work together to develop the carbon accounting protocols and policies that are needed to bring more capital to fund high albedo projects at scale. I thank you for being here today and for being a part of a movement to build momentum for a practical multi-benefit solution to climate change. We are excited for the panel discussion, which for the first time is bringing together the world's 4 leading experts on the subject of high albedo surfaces and negative radiative forcing to reduce the greenhouse effect. Some climate nerds, myself included, have referred to this panel as an albedo supergroup. Through their peer-reviewed research, our panelists have quantified albedo's benefits in the form of carbon dioxide equivalency, CO2. Quantifying these benefits in terms of CO2e could offer a path forward for developing policies and programs that encourage the funding of cool surface projects in exchange for a form of carbon credit. I'll seed that idea with you all for now, and we'll save that for a future discussion. With that, I'd like to introduce our moderator, Roel Hammerschlag, who is principal of Hammerschlag LLC, specializing in greenhouse gas inventories, greenhouse gas regulation, and life cycle assessment of fuels and renewable energy technologies. Mr. Hammerschlag has served Washington State as the program manager for the state's energy strategy and has served the Stockholm Environment Institute in the role of senior scientist. He's applied his highly specialized knowledge in physics, thermodynamics, and life cycle assessments to evaluate an enormous spectrum of energy resources, from solar PV to cellulosic biofuels to genetically modified algae. Most recently, his manuscript entitled Bringing the GHG Market has been accepted for publication in the Journal of Carbon Management. Mr. Hammerschlag has a Bachelor of Science degree in physics from the Massachusetts Institute of Technology and a Master of Public Administration degree from the University of Washington. And with that, I will now turn it over to Roel to moderate the panel discussion. Roel?
Thanks, Bryn, and welcome everyone. Today we're going to have 4 15-minute talks, each followed by a short question and answer session. So let me start just by quickly introducing the panel so you know who's who. So first we're going to start with Dr. Maria Hokuba. Can we bring her onto the stage?
Hello.
And Dr. Hokuba will explain the basics of why albedo matters. Next, we'll have Professor Hashem Akbari. Can we get him up? Dr. Akbari will be detailing the connection between albedo's impact on climate and the greenhouse gas impact on climate.
Good day, everybody.
All right, and next we have Dr. Hassam Azari Jafari, and he'll be discussing the modeling of albedo impacts in urban environments. And then last but not least, we have Dr. Ronen Levinson, who will be talking about the surface technologies we can use to manage urban albedo.
Good morning, good afternoon, everyone.
All right, great. So we have the whole panel up. Congratulations to congratulations to us on getting the technology working. All right, we want to keep this dynamic for you all, for the audience. So we'll have each of these 4 folks go through a roughly 15-minute presentation. And as they speak, please feel free to submit questions. And then we'll have a little question and answer session after each one. And I'm going to share my own screen here for just a second so that you can see how to do that. So you should see my screen. Oh, look, that's anyway, you can still see what's happening. So you have this, you may have a chat button down here. I'm not sure whether you do. If you don't see this panel on the right, you will want to press that chat button, and then you'll see this panel on the right, and there's a Q&A option up here. So if you work in this chat area, you'll be speaking with the people at your table or in the audience. But if you press Q&A, you will be submitting a question for the speaker. So if you have a question for the speaker, please press this Q&A button, and then you can enter your question right down here and press ask to submit the question. So please feel free to do that while we're speaking. With that, I think I'm going to go ahead and introduce Dr. Hakuba in a little more detail, and she'll get going. She's a research scientist in the Aerosols and Cloud Science Group at NASA's Jet Propulsion Laboratory, where she's Deputy Principal Investigator for NASA's satellite mission Libera, which provides continuity to the Earth radiation budget climate data record. She also leads a project that investigates the feasibility of measuring Earth's energy uptake through radiation pressure variations in orbit, and studies various aspects of climate using satellite, surface, and modeling data. So Dr. Hakuba, go ahead and share your screen and you can get started.
Thank you very much, Ro. First off, do you see my slides?
Yes,
Awesome.
we do.
There we go. Thank you very much for the nice introduction and inviting me to this very important event. I welcome everybody warmly to my presentation on Earth's radiative energy budget, or in other words, a planet out of balance. And let me start with one of many schematics that exist to summarize or illustrate in a simplified way Earth's energy budget, or in a global Earth mean way. So there's basically three main flows or ways that energy can enter or exit the Earth system. The main source of energy to Earth is, of course, sun's radiative energy flow into the Earth system, and sun's energy can be absorbed by the surface and by the atmosphere, for example. There's two main ways of flow of energy out of the Earth system and back to space. And on the one hand, that is the reflection of sunlight from the surface, from clouds, from particles in the atmosphere. And about 2/3 of the sunlight into the Earth system is absorbed by the surface and the atmosphere, and about 1/3 in the annual global mean is reflected back to space. And on the other hand, we have Earth's emission of thermal or infrared radiation that leaves Earth. And this is also the part of the energy budget where the radiative forcings occur that perturb the radiation budget and yield global warming through the radiative forcing of added greenhouse gases. So we all already know that by having added more greenhouse gases, we have added an agent that absorbs and re-emits more of this infrared radiation back to the surface, which is key to understand global warming. And I might talk about this a little more later if we have time. So first, let me talk about the main ingredient of energy input into the Earth system, and that's the sun. Sun is extremely hot, and it emits mainly in the visible portion of the electromagnetic spectrum. And interestingly, evolution made it that our eyes are sensitive to this part, but that's not what we're talking about today. But about half of this radiation emitted by sun is in the visible spectrum. But integrated over the entire solar spectrum, integrated over the Earth and the annual mean, the energy that we receive from Earth amounts to 340 watts per square meters. What this number means, so per 1 square meter Earth, we would be able to power half of a microwave. And integrated over the entire Earth's surface, we would be able to run 90 quadrillion microwaves with the energy that sun emits and Earth receives. So the other very important component that we talked about is Earth emitting infrared radiation. Earth is way cooler than Sun, so it emits radiation at a different part of the electromagnetic spectrum, and this radiation is not visible to the human eye. Averaged over the globe and over 1 year or multiple years, Earth emits about 239 watts per square meters back to space, and this amounts to about 1/3 of a microwave per square meter. And like the solar radiance that I showed earlier on this slide, Earth's radiation is measured by NASA satellites, currently the Clouds on Earth's Radiant Energy System. If you have questions about the satellite missions, we can talk about that later, but I won't talk much more about it here. So as I said, infrared radiation might not be visible to the naked eye, but it is if we use infrared cameras. So here are 2 examples, the lady to the right, to the left, and a little polar fox to the right. And it is interesting to note here that the hotter the surface is that emits infrared radiation, the brighter it is in terms of infrared radiation. So that lady appears to have a quite warm forehead, while her hair nicely insulates her scalp. And that's even more pronounced for this polar fox. The very warm coating insulates its skin from emitting the infrared radiation, and it's mostly the eyes and the open mouth. So the emission of infrared radiation is largely a function of temperature. So, and that brings me into talking just briefly about the greenhouse effect and the atmosphere acting as a nice blanket on a cool winter night. And it is important to note that the atmosphere and the gases therein are very important to maintaining a comfortable temperature on Earth. Without the greenhouse effect altogether, Earth would be way too cold to be habitable. Okay, so right now, or before the worst of emissions has occurred, we call it sometimes pre-industrial period, before human input of greenhouse gases into the atmosphere, the greenhouse gas amount in the atmosphere was quite comfy. Since we have started adding greenhouse gases, we have decreased the emission of infrared radiation, or in other words, we have increased the absorption of infrared radiation that would like to leave Earth. These molecules, they tend to absorb a photon of infrared radiation, they start vibrating, and they randomly re-emit this photon, either to space, either towards another molecule, or towards Earth. So by adding more of these molecules, we are thickening the blanket that the atmosphere is to our planet. So the other part of how Earth loses radiative energy is by reflecting sunlight directly back to space. And there's multiple pathways that Earth can facilitate this. It's important to note that during night, for example, when there's no sunlight, no reflection will occur. And that's in contrast to the emission of infrared radiation, which occurs at all times of the day, according to Earth's temperature. There's multiple different types of surfaces on Earth. Some are darker than others. For example, the ocean, which covers a vast amount of Earth's surface, about 70%, is a very dark surface and mostly absorbs solar radiation. So it reflects for sure less than 10% of the solar radiation that it is subject to. Some of the brightest surfaces on Earth are snow-covered surfaces, ice on land, and sea ice on the ocean. And those surfaces are very reflective. They reflect anything. Here I have an example. I'm saying about 80% and more of the sunlight that it receives is reflected back to space. And clouds, likewise, to satellite instruments, they often look very similar to a snow-covered surface or ice sheet, very reflective, cover about 70% of Earth's surface, and especially reflective over a dark surface like the ocean. So altogether, all these ingredients together make Earth reflective to about 30% of incoming sunlight in the global annual mean. And that's about 100 watts per square meter in the year per year. Now that we have all the different ingredients of Earth's radiation budget, we can put together Earth's energy balance or imbalance. So input from the sun, radiative energy input into Earth system, 340 watts per square meters, is partly compensated by energy loss through reflection and partly compensated by the emission of infrared radiation. So in times where there's no global warming occurring, energetic equilibrium should be present, and these three components should add up to zero. Currently, observations have told us that over the observational record of about the past 20 years, we've measured a radiative energy imbalance of about plus 1 watts per square meter, meaning there's a surplus of energy that Earth is currently absorbing. And this number equates to 130 trillion microwaves that could be powered with this annual mean rate of energy uptake of 1 watts per square meter. Or in other words, in the words of the latest IPCC report, this rate of energy uptake of 1 watts per square meters is the same or equates to about 20 times the annual rate of global energy consumption in 2018. Imagine we could harvest all this energy, all our problems would be gone in terms of energy consumption, obviously. So we've been talking about radiative forcings through greenhouse gases, through changes in Earth's albedo. And these radiative forcings yield a warming of Earth's surface, Earth's atmosphere. And at the moment, there's other forcings also through injecting particles into the atmosphere. If in the IPCC report, when you add all these radiative forcing effects together, there's a surplus of 2 watts per square meters. This is in part combated by feedbacks, climate feedbacks, that occur in response to the warming of Earth. So we're warming Earth through radiative forcing impact, and the feedbacks either act to diminish this initial climate response to the radiative forcing or act to even amplify it. So as we talked about before, when Earth warms, it will tend to emit more infrared radiation. So this is a negative feedback. Some of this energy will be emitted back to space. And then there's positive feedbacks. For example, we know a warmer atmosphere will become moister and will absorb more infrared radiation. And
5 minutes left, Maria.
5 minutes. Okay, that's all right. Another feedback is that by warming Earth, more ice melt will occur. This will reduce surface albedo and lead to more absorption of solar radiation. So that's an amplifying feedback. With clouds, we're not so certain yet, and we can discuss this later. Altogether, right now, it looks like the feedbacks are trying to compete with the radiative forcing. But taken together, this is how the current Earth energy imbalance is constructed from. And it is positive, and Earth is heating up. And some of the more known symptoms of a positive energy balance or of these radiative forcings I've summarized here. For example, of course, the heating at the surface and associated changes in what we call extreme events, more intense, more frequent droughts, or storms, for example. We've also have records that tell us very robustly that sea level is increasing, and with this associated is more severe flooding events, for example. And to the right, I'm showing the impact on biodiversity that a decrease in sea ice brings with itself. But as I said earlier, it's also a very important climate feedback that even amplifies the radiative forcing of greenhouse gases. Now, knowing all this and the different pathways that perturb the radiation budget, how can we reduce the energy imbalance to become closer to zero and cool the planet? So one way, or it's a combination of ways, is through greenhouse gas management. And we want to reduce the absorption of infrared radiation in the atmosphere and the re-emission towards the surface, which means we have to either reduce the emission of greenhouse gases, find a way to capture the CO2 and store it away, for example, in the deep underground. And reforestation has also been brought up as a way to bind carbon or CO2. Another very potent way could be by increasing the reflection of sunlight, and that's what especially the other panelists will talk about in more detail, is urban management. And there's also cropland management, which is not the topic of today, and other ways of increasing Earth's reflection. And with this, I would like to thank you very much for your attention. And if you have questions, I am happy to take them now, or please send me an email. Thank you very much.
All right, thank you. Right now there are no questions in the Q&A list. If any of you in the audience have questions about that material that Dr. Hakuba just related, please type them in. I'll give a minute or two for that to happen. Maybe I can see things. Oh, here we go. We've got our first. So the first question is from Michael Harrodson, where urban areas are a small fraction of Earth. How could it impact the energy balance?
I know that Hashem did a lot of research on that. If you want to take it, Hashem.
Hashem Akbari. And urban areas constitute about 2% of the land surface area. And as I will discuss a little bit later on, basically the problem of global warming and climate change has been created by emission from one car, emission from one factory. And the solutions to that is also by a portfolio of different technologies, which probably should include by the reduction of the CO2 emissions at the beginning, and also by the reflection of the sunlight. And every meter square of a surface reflecting certain amount of sunlight would help to reduce the global temperature. And when there are many, many hundreds of square kilometers of the surface areas having a high reflectance, it would start having some effect. And if you are patient enough, I would be able to show you some numbers to kind of satisfy your thirst.
Yeah, and I would like to emphasize that Dr. Akbari is going to get into more detail in this in his talk as well, which is just about to start. And I'd love to add myself that or get you ready for hearing that the albedo management can have approximately the same order of magnitude impact to climate as greenhouse gas management in the urban setting. So as Dr. Akbari was just hinting at, there's a large spectrum of solutions we're all working on for climate change, and this is one of them. And cities are doing their best to contribute. And all of the folks on this panel believe that managing albedo is a way that cities can contribute that is just as valuable as managing greenhouse gases. No more questions in the queue. So to keep things moving timely, and we did start a couple minutes late, so let me just go ahead and move on to introducing Dr. Akbari in more detail, and we'll get his presentation started. So Hashem Akbari leads the Heat Island Group at Concordia University in Montreal, Canada. His research is focused on analyses of energy, air quality, health impact, and environmental aspects of heat islands and heat island mitigation measures. His advocacy for cool surfaces covers many decades, including being the founding organizer and the board member of the Global Cool Cities Alliance. With the Alliance, he's currently coordinating the 100 Cool Cities initiative to cool urban heat islands and counter global warming. So, Dr. Akbari, we're ready to hear from you. So go ahead and share your PowerPoint screen when you can.
Good day, everybody. I hope that you all can see my presentation. And this year is the 38th year that we started this research and analysis initially at Lawrence Berkeley Lab. And at that time, we were the only group in the world just a short decade later, there were more than 10 international institutions following suit. And now the number of institutions following this topic has increased to hundreds. So I'm going to give a little bit of background adding up to what Maria said. And if you look at the remote images of various urban areas, you typically see that there are impermeable surfaces made of pavements, and roofs typically add up together in most urban settings to about 60 to 70% of the total urban area. All these surface areas are man-made, and they're typically in darker color than their suburban areas. So our objective is that if we can improve the reflectivity of these surfaces, how it would affect the energy consumption, the local climate, and also ultimately its impact on the global warming. So a little bit of background, that we have done many analysis, both theoretical as well as experimental, showing that by cool roofs, keeping the roof cool and reducing heat conduction into the building, that can save energy of the buildings by typically about 20% of the energy, air conditioning energy used for the areas under the roof. And now in an urban setting, cool roofs and cool pavements would reflect more of the incoming solar radiation, and the surfaces do not get as hot, and the air that it is also brushing on the surfaces would not get that hot. So that would reduce the ambient air temperature, and it improved the air quality, urban air quality. It improves the citizen comfort. It reduces mortality during the heat storm. On top of that, if the surfaces within the urban areas, and that can also be extended to non-urban areas, by having more reflective surfaces, they can reflect the shortwave radiation directly back to the atmosphere, and that is independent of the CO2 cycle. And this is known as the Geoengineering 101. The reason that we are calling it Geoengineering 101 is because these technologies of the reflective surfaces have been used in many parts of the world in the last thousands of years, and we know that there are no negative consequences to those. So the way that thinking goes like that is like this: changing albedo and of urban surfaces and changing atmospheric CO2 concentration both result in change in radiative forcing. And comparing these effect of these two radiative forcing, one can create equivalency between the CO2 reduction as well as the changing of the albedo of the surfaces. Let me explain a little bit more and expand what Maria introduced very nicely. About 340 watt of energy that is entering the outside the Earth's surface, outside the Earth's atmosphere, about 77 on the average are being reflected by the clouds and the atmosphere, and the remainder of that is either absorbed by the atmosphere or coming to the surface. and altogether about 30% of the radiation from the surface is reflected. So if you add up this 30 and the 77, about 1/3 of the solar energy is either reflected by the clouds or reflected by the surfaces. So our wish is just to reflect the radiation from the surfaces a little bit more, and that is the calculation that we are going to see how it would affect counter the global warming. So we did a series of analysis, and these analyses are based on climate circulation models, and we perform climate simulations and following the Earth's temperature on two different scenarios. One is business as usual scenarios that would be basically continuing emitting of the CO2 gases and other greenhouse gases into the atmosphere. This is known as business as usual. And then one is based on the aggressive mitigations. And as you see on the black curves on both sides of this, on the business as usual, the temperature on the Earth would exceed 22 degrees Celsius by 2 centuries from now, and then perhaps 3 centuries from now. And then if we do an aggressive mitigation, it would stabilize but around 16 degrees Celsius. Now, if we increase the reflectivity of the land areas within plus or minus 20 degrees of the equator, or plus or minus 45 degrees of the equator by 0.1, then you would see that the temperature of the Earth is responding on the long term to this long-term radiation reflection plans. And as a result of that, you would see that the temperature of the Earth under the aggressive scenario would be reduced by about 1.5 degrees Celsius by changing the reflectivity by 0.1 within plus or minus 20 degrees, by about 3 degrees within plus or minus 45 degrees. And the same is being observed when you are doing it for the business as usual. So this gives us a little bit of comfort that the albedo management, to a certain extent on the long term, is independent of the scenarios of the CO2 managements. So this is for changing the reflectivity of the Earth for a large areas of the land. But once we start normalizing these numbers per square meter of the areas, we would get a strikingly very, very comparable result that if you look at the business as usual or aggressive mitigation, you would find out that the temperature of the globe would respond by a very tiny amount of minus 3 times 10 to the minus 15 Kelvin. And that is a number that it is probably not digestible by an average citizen. However, when you look at the equivalency of this to CO2 emissions, you would find out to a very strikingly interesting number of about 7 kilograms of CO2 equivalency to increasing the albedo of the surface of a meter square of a surface by 0.01. So that would mean that on a typical house, if you increase the albedo of a surface by 0.01, which is a very, very small amount, and I would show these numbers in more detail later, you would be able to have an effect, if that house is 100 meters square, of effect of about 700 kilogram equivalency CO2 reduction. This
5
number,
minutes remaining.
pardon me?
5 minutes remaining.
Sure, no problem. So we continued with this analysis and going forward, saying that if we have a typical age-wide roof compared to a typical dark roof, that would increase, would be showing a reflectivity improvement of about 0.40. So that is an equivalency of about 280 kilogram of CO2 per meter square. So saying it the other way, for every 4 meters square, it is an equivalent CO2 emission of about 1 ton. For the slope roofs, you would be having a smaller chances for improving the reflectivity because of the static, and that number is lower. And for pavements, going from a dark asphalt to a light concrete reflectance, you would be having an effect of increase of CO2 equivalency reduction of about 100 kilogram per meter square. Now let us expand these numbers to a worldwide area. A typical area of a city is about 25% roof, 35% paved surfaces. So we estimate that the total urban areas worldwide is about 1.5 million kilometers square. And then of that, about 3.8 times 10 to the 11, or 0.38 million kilometers square are the roofs, and 0.5 million kilometers square are the pavements. So then if you extrapolate these numbers for the entire surfaces, you would find out improving the roof reflectivity would counter 67 gigaton of CO2. Improving reflectivity would counter 56 gigaton of CO2 for a total of about 123 gigaton of CO2. Now, what does that mean? That 150 gigaton of CO2 is over 4 years of the world emissions. So the current world emission is 37. 150 gigaton is equivalent to 4 years of that. It is equivalent to the emissions of all the cars for the 60 years. It is equivalent to 1.5% of the emissions growth over the world, and for 25 years. So as you see, these numbers are very, very striking, and that's the reason that the world has responded, and IPCC has adopted the equivalency of 7 kilogram CO2 per meter square per increase of albedo of 0.01. So what are the values of that? If currently in Europe, CO2 is being traded at about $25 per ton. So 150 gigaton is worth $3.7 trillion of dollars.
1 minute remaining.
Yes, and then this would be adding to about $5 trillion of dollars in air conditioning savings over the next 100 years. So I think that Ronan would also talk about the Global Cool City Alliance, but we have established Global Cool Cities Alliance that its mission is to promote cool roofing and cool pavements throughout the world. So they do have an extensive partnership that would include something like about 100 nations nowadays. So the conclusions that I would like to make is that these policies that are being designed based on the data are very, very effective, and pursuing these policies would have good results on the consequences for the globe. And with today's ruling from the Supreme Court in the United States, I would like to make this distinction that we as citizens constitute the world. We have made the world where it is right now, and we can introduce changes. So we are the people in the driving seat, and we should be able to be following and selecting policies that would affect countering global warming. With that, I would conclude my comments, and I would be more than happy to answer any questions.
Great. Thank you, Dr. Akbari. We do have a few questions. So first of all, from Michael Harrison, the gigatons reduction from cool roofs does not include the greenhouse gas savings of reduced air conditioning. Is that correct?
Will you please repeat the question? I'm not sure that I got it.
The equivalent gigaton CO2 reductions you reported in your presentation, those are only due to the albedo to the reflected radiation, and do not include reductions associated with less building energy demand.
That is absolutely correct. That is absolutely correct.
Okay. Austin Kerr asks, in the math that equates increasing albedo to an equivalent CO2 reduction, over what period of time would this equivalency occur?
As you see, there are two parts to the answers to that question. The equilibrium condition, if Earth would respond to the conditions changes immediately, you would have an immediate effect. But as my curve showed, the equivalency, about 80% of that would happen within the first 20 to 30 years of the changes. I would go back to my slide in here. If you see on the lower curves that out of that 7 kilogram CO2 equivalency, within the first 20 years, you would see about 5.5 kilograms of it.
Okay, great. Let's see. I'm trying to the feed changes my list of questions based on the upvotes. So I'm losing track of who came in what order, but let's see. How do you, Mark is asking, how do you compare cool roofs and pavement to green roofs, walls, or ground with vegetation?
In terms of the albedo management, green roofs are basically considered dark surfaces. That would mean that they would absorb most of the short-wave radiation, and then it has to follow the route of the thermal emissions from the Earth's atmosphere. In terms of the energy saving potentials, green roofs and cool roofs have more or less the same effect. The only difference between them is that the cost of a cool roof is basically is zero. The cost of the green roofs may be in hundreds of dollars per square meter. That's incremental cost.
Okay. Another question we have is from Gabriela Sosa. What would it cost in CO2 to replace all the roads and roofs to cool? I think she's asking what's the greenhouse gas reduction equivalent of all roads and roofs being replaced?
Yeah, I think that I gave that number in here based on my estimate in the study that I did in 2012 for roofs. It is equivalent to 67 gigaton of CO2, which is about 2 years of the world current emissions, and for pavements is about 56 gigaton of CO2, which is about under 2 years of the world emissions.
Yeah, and there's one last question. This might actually be something for discussion near the end of the set of presentations. The question is, as there's so much evidence of the benefits of cool roofs and pavements, why aren't more places implementing these? So that's a very interesting policy question. And all of the speakers on the panel have had some experience interacting with policy. So I'm inclined to let's address that question after Ronen's presentation, because I think all of the speakers will have some interesting views on that. So I'm going to keep that in mind.
I concur with that because there is not a short answer to that question.
Yeah, right, exactly. Okay, let's move on to Dr. Hessam Azari Jafari. He is a lecturer at the University of Michigan and a research affiliate at the Massachusetts Institute of Technology. His research has focused on the life cycle impacts of cool pavements, circular economy, and construction materials. His connections to albedo management go back to his PhD thesis, assessing the implications of albedo for the environmental impacts of pavements from a policymaking perspective. All right, Dr. Azari Jafari, you ready to go? It looks like you are.
All right. Hello, everyone. Thank you very much for this introduction, Royal. I'm glad to be here to share some of our results on the cool pavement implications on the climate change impact and how much we can save as a result of implementing these cool pavement strategies at the local level. This is a collaborative work with multiple climate scientists, graduate students, and also systems experts. To start this presentation, as other presenters and speakers elaborated, we are thinking about the albedo and changing the surface reflectivity of the pavements, which is the fraction of solar radiation that is reflected from a specific surface, in our case here, focusing on the pavements. And we realized that as a result of increasing the pavement albedo, we will store less heat on the pavements inside the body of the pavements, and therefore we have also a lower surface temperature. And this surface temperature reduction will eventually lead to reducing the ambient temperature, which is a counteraction to urban heat island effect, obviously. But what is also very important for us to discuss here is reflecting more energy by making pavement albedo increased. Therefore, we give this climate benefit in terms of a negative radiative forcing. And the topic that I wanted to discuss with you and the key messages that I would like to share with you is that, first of all, radiative forcing effect on climate change can be estimated at local scale. I'll show you the example of the city of Boston and also different locations in the United States. Second one is the impact of pavement albedo on climate change is significant. I'll bring you some examples to show you to what extent it can be significant when we are assuming and calculating the pavement albedo impact on the climate change. And also in urban settings, I would like to pay your attention to two different phenomena. One is the city configuration that can affect the intensity of the savings, and also the building energy demand as an addition to radiative forcing effect that we could expect in urban roads. Okay, let's start talking briefly about why albedo is important for us. The other presenters, Dr. Hakuba and Dr. Akbari, will mention about the mechanisms here, the radiative forcing, and whatever we use to change or whatever we use to change the energy balance, we would have some implications on the global warming. And that's what we call here as climate forcers, such as greenhouse gases. So we know that these greenhouse gases have some capabilities to store heat. So solar radiation will be stored in these greenhouse gases, and it makes our planet warmer. We have aerosols, the same mechanism, and also the surface reflectivity of our surrounding neighborhoods, including our built environment, which is very important for us. So if we change the surface reflectivity, we will change this radiative balance, and we will induce a climate change benefit. For that, for the calculation step, I just want to show you an example how methane global warming impact here, GWI, is being calculated. So we talk about the amount of radiative forcing that can be absorbed or can be stored by these greenhouse gases. For example, 1 kilogram of methane, and we would like to normalize it and find the number as opposed to carbon dioxide, 1 kilogram of carbon dioxide. So we sum up the cumulative radiative forcing by methane here, which is the green area under this curve, and divide the value by the cumulative radiative forcing by carbon dioxide. And it will give us kilogram CO2 equivalent for 1 kilogram of methane gas emissions. Analogous to that, if we increase the pavement albedo, we will induce a negative radiative forcing. We make our planet cooler, we make our surface area cooler. And if we sum up the radiative forcing of the albedo change for that specific surface area during a finite time horizon here, as you can see on this orange part of this chart, this part up to 40 years, for example, the albedo was maintained 0.2 and gradually changed as a function of time because of the wear and tear of the trucks and tires and everything. We will induce a negative value of radiative forcing. And if we sum up this value and divide this by the equivalent amount during this time horizon for carbon dioxide, we have the kilogram CO2 equivalent savings we could expect from the pavement albedo change, only for radiative forcing. So for that, obviously, we need to quantify the radiative forcing, as you mentioned. And as Dr. Akbari and Dr. Hakuba well mentioned, we need to have a good understanding of what's going on in terms of the incoming and outgoing solar radiation. And for that, we have to calculate and have a good estimation of the atmospheric transmittance based on the location, obviously the longitude and latitude, to better understand what's the angle between the solar sunlight rays and also, for example, the perpendicular line to our surface, or the cloudiness, as well as the amount of air particles, and most importantly, the pavement albedo, to have a good calculation of the incoming solar radiation, the amount of solar radiation received by the pavement surface. Then the albedo will play a role, and we have the outgoing solar radiation from the surface. And then we have some reflection and absorption by clouds and everything that we have in the atmosphere. Greenhouse gases in urban areas are important here. And then at the end, considering the changes that we induce in the system because of the albedo change, we are interested in knowing how much radiative forcing at the top of the atmosphere, the outgoing radiation will change. And this is give us an idea about the radiative forcing of the pavements. Here is the results of the radiative forcing induced by 0.01 albedo increase for 14 different locations over a 50-year analysis period. On the x-axis, you can see the city names. On the y-axis, the left one, you can see the amount of global warming impact savings in terms of kilogram CO2 equivalent per square meter. And here on the second y-axis, you can see cloud transmittance or cloud factors here. And you can see that from Miami here, we have a more significant number, 1.5 kilogram CO2 equivalent per square meter of the pavement, as opposed to Minnesota, Duluth, that we have relatively a smaller number because of all these climate parameters and changes that we would expect. But these are all climate savings, so we save some CO2 equivalent number as a result of increasing the pavement albedo. You can go to this link. I will share the slides later, so you can have access to this link and then go and find the appropriate number for your location in this Tableau dashboard that we developed on our website. So in a nationwide level, we continue the same analysis, and we estimated the amount of climate change savings as a result of the albedo increase for the whole pavement network in the United States, both in the urban and rural areas. And you can see that the intensity is quite different, obviously, for Texas and California because of their very extensive road network. We expect more significant amount of savings as a result of the albedo increase for 1 year. But if we sum up all these values, this number would be really large, and it's equivalent to around 3.7 million ton GHG emissions, 3.7 million ton car GHG emissions, which is around 3.2% of the passenger vehicles in the United States. So it's a sizable amount of GHG savings that we could expect as a result of the albedo increase for pavements only. And obviously for Texas, it's also, like I said, it's very large, equivalent to 347,000 vehicles emissions, which is around 4.1% of the passenger vehicles emissions for a given year in Texas roads. So we have to think about it because it's significant, because it can make a big change in our climate change policies. But what is different in urban areas? Like in urban context, we see that we not only have the horizontal infrastructure systems, but also we have vertical elements in our built environment, such as buildings, trees, and these elements will provide some shading and trapping effects. For example, the incoming solar radiation in densely built neighborhood is around 30% of the total solar radiation that will hit the pavement surface. In suburban areas, almost 90% of the total incoming solar radiation can be received by the pavement surface. Therefore, if you want to have a more concise estimation of the amount of incoming solar radiation, and therefore the radiative forcing, we have to definitely consider the urban density and city texture in this analysis. To show you some results, here is the analysis that we did for the city of Boston. And you can see different neighborhoods separated from each other, census tracts. And we assume that the albedo increase happened from 0.1, a typical dark asphalt pavements, to 0.3, a more reflective pavements. We have different options, including concrete pavements, reflective asphalt, or reflective concrete itself. And during a 50-year analysis period, while we see that we have savings in terms of radiative forcing effect and in terms of GHG and climate change impact, the savings can be quite different from one neighborhood to another. On the
5
right,
minutes remaining.
Sure. On the right part, you can see the downtown area. The amount of radiative forcing saving is around 26 tons CO2 equivalent per lane kilometer, while in a sparsely built neighborhood, the number can be 2 times larger, around 69 tons CO2 equivalent per lane kilometer of the road if we increase the albedo from 0.1 to 0.3. So it's very important to capture the context and the city texture when we are calculating the radiative forcing effect. So far, we discussed the amount of surface reflectivity and radiative forcing, meaning that the amount of solar radiation that will be reflected back to the top of the atmosphere. But when we have buildings in that surrounding neighborhoods, we have some of those reflected solar radiations hit by the building envelope, and some of them will be absorbed by the pavements. And as we discussed, it's going to contribute to mitigating the urban heat island effect. One of them here, we call it as building energy demand effect, the incident radiation effect, and the other one is building energy demand cooling effect. So the cooling effect will obviously decrease the temperature in urban areas and will eventually reduce the cooling demand, but increase the heating demand in winter seasons. As opposed to incident radiation effect here, that makes our building envelope warmer, therefore we have more cooling demand, but less heating demand in winter seasons. If we sum up all these values together for the same case study that I showed you for the city of Boston, you can see this is what I have already shown you, the map, the radiative forcing impact of the albedo increase. I added the building energy demand, the BED impact of albedo increase, and you can see that in some census tracts or neighborhoods, we have savings in terms of the GHG emissions from the air conditioning system, but in some other neighborhoods, we have excess GHG emissions. Here, we showed it with red colors. But if you sum up all these two effects and the climate change impacts from this radiative forcing impact and building energy demand, we can see that we still have a uniformly safe CO2 in different locations in the city of Boston. More specifically, if we zoom in to the downtown area, we can see that the amount of savings will be intensified if we consider both the BED effect and radiative forcing effect, implying the importance of considering the whole mechanism and also giving a picture to the policymaker or decision maker where to start to gain the most benefits out of the albedo increase. Getting back to my previous key messages, radiative forcing effect on climate change can be estimated at local scale, a pavement segment level, and the impact of pavement albedo on the climate change is significant, showing the number equivalent to the amount of passenger vehicle emissions. And in urban settings, it's important to consider the city texture and the city configuration, as well as the building energy demand, the amount of cooling and heating load changes as a result of the albedo increase in the adjacent pavements. With that, I would like to thank you for joining me for this presentation. Here is my email address. I'd be happy to take any questions. And for further information, I have listed some of our publications in this area of research. Thank you.
All right, thank you very much. We have a number of questions in the queue. The first one from George Walker is, what's the delta between the greenhouse gas equivalent offset of a square meter at the equator versus the greenhouse gas offset of a location further from the equator?
I can comment on the case studies that we have conducted in the US. We haven't gone beyond the US geographical context, so I don't have a specific number for that. But for the US, it can vary up to 50% from the southern location to the northern location in terms of the amount of radiative forcing savings.
So Austin Kerr is asking more specifically, in slide 7, is the difference in the values for Miami and Minnesota explained by the angle of the sun, which is the same question, I believe.
Exactly. So, like I said, there are multiple climate parameters that will intervene and will change the intensity of the savings coming from the radiative forcing effects. So some of them are related to the solar zenith angle. Some of them are related to the density of the neighborhoods, greenhouse gas emissions, the amount of traffic on the roads is also very important. So this intensity depends on multiple context-specific parameters.
Okay, great. I'm looking for the next unanswered questions. Okay, Michael Harrison, it says, following the question on green versus cool surfaces, do urban trees along the streets really help? What is the net GHG of their absorbed GHG versus added dark surface?
Definitely, I think we have multiple solutions to overcome the albedo, the albedo impact and our dark urban surfaces, including the green vegetations, and providing other solutions related to the pavements, and as the other presenters mentioned about the cool roofs. Some in some cities and in very well established areas, it's really difficult to change the city geometry, the canyon geometry, and changing and converting pavements to, for example, urban vegetations is quite difficult and probably impossible in many cases. So in those cases, we don't have any choice rather than being flexible and focusing on our pavement solutions and find the most appropriate options to benefit from the pavement albedo or mitigate the albedo impact.
Okay, next question is, you calculate some Boston areas will need more heating if pavements are whitened. Was this calculated for the present day or a future warmer climate?
For this analysis, we only focused on the weather data that was provided historically from the Energy Plus platform. So you could imagine that it's the historical data that we observed and we used for our analysis. But the future increase in the temperature would be an interesting area of study, that how much the future increase in the temperature would contribute to this analysis and the urban heat island effect. That's a good point.
And then a pair of related questions that, again, we might want to expand on after the talk, after all the talks are complete. One of them being, wouldn't there be a high carbon cost associated with replacing all of these surfaces? And then Morgan Rogers is, sorry, that was, I'm losing. And then Morgan Rogers is asking, are there potential trade-offs we should be considering? So it's in the same domain there.
Right. Well, my background is on construction materials. Maybe I can expand it a little bit as well for especially pavement examples. And I'm sure Ronan will explain in more details about the technologies to use for improving and increasing the surface albedos. But specifically for pavements, we have, well, pavements are composite materials. So they have one part of stones or aggregates, and the other part is the binder itself. And this will give us the flexibility how to build our roads and what material choice will give us the most benefits. For example, you can use a query source of aggregates coming from, a lighter color aggregate sources. Therefore, we increase the pavement albedo by changing the query from one location to another if we have it locally available. It really comes at no cost, actually. But we can have different options such as reflective coatings. You can see the examples in different cities, city of LA, city of Phoenix, Tucson. Or, for example, we can make the binder reflective, shifting from, for example, a darker binder to a lighter color binder. For example, in concrete pavements, we can use this byproduct of steel industry called blast furnace granulated slag to be replaced and to be used as a replacement of Portland cement. And it makes a huge amount of albedo increase to 0.6, for example, that we use, and we make the pavement even more reflective. So we have multiple options. It can reduce the embodied emissions of the pavements even, but it depends on the local availability of materials and resources.
Okay, great, thanks. There's a couple more questions in the queue, but I'm going to save those for after Ronan, because I want to make sure we get all 4 speakers into the intended time for the presentation. So So Dr. Ronan Levinson is a staff scientist and leader of the Heat Island Group at Lawrence Berkeley National Laboratory in Berkeley, California. Within his research portfolio, he develops cool roof, wall, and pavement materials, improves methods for the measurement of solar reflectance, and quantifies the energy and environmental benefits of cool surfaces. So, Dr. Levinson, please go ahead whenever you're ready.
All right. Can you see my screen?
Yes, it looks
Excellent. All right. So thanks very much for the opportunity to talk to you. I'm going to speak about how to make bright choices about roofs, walls, and pavements. So let's talk about the what, where, and how of selecting solar reflective cool surfaces. What cool options are available for roofs, walls, and pavements? Where should cool surfaces be used? And how can you find cool surface products? Because if we're going to follow the advice given by the previous three speakers, we need to choose some materials. I've put together a little matrix of pictures of some of the sorts of cool solutions that are available today. And the first thing to note is that reflective roofs, walls, and pavements are available in light, medium, and dark colors. So, for example, the classic example of a cool roof is a white roof membrane. That's actually pretty common in the United States. In other parts of the world, white roofs come in the form perhaps of limestone. This is a photo from Bermuda, where limestone roofs are part of collecting rainwater. And then cool color roof tiles are very common. This is a picture from abroad, but if you just travel through California and the rest of the West, you'll see lots of Spanish architecture involving natural red clay tile roofs. In recent years, we've seen the advent of cool color asphalt roofing shingles. These tend to look very similar to traditional asphalt roofing shingles, and asphalt roofing shingles are the dominant roofing product for pitched roofs in the United States, so that's an important player. We've since thought about another dimension for cool surfaces. Let's move from the horizontal to the vertical and think about walls. Now, light-colored walls are really quite common. If you were to look around at buildings in your city, you might find lots of dark roofs, but you'll find that it's not unusual at all to find a light-colored wall. But as I'm going to explain in a moment, you don't necessarily have to use light colors if you want to reflect sunlight. In this next picture here, I have an example of a wall that was treated with a cool color exterior paint. For pavements, the fundamental options are to look at a coating, which could be white or could be in some exciting color, or to look at changes to the structural material. For example, in the picture at the lower right, we have at the top ordinary asphalt concrete. That's what most of our streets are paved with. And in the bottom part, we have cement concrete, and you're familiar with that because that's what you walk on when you stroll on the sidewalk. I mentioned a moment ago that not all cool surfaces have to be white, and here's why. Our eyes are really good at detecting sunlight, but we only detect sunlight in the band where it's most intense. So I've colored that green here. This is the visible part of the solar spectrum. And a bit of the sunlight arrives in these shorter ultraviolet wavelengths, but about half comes at these longer than visible near infrared wavelengths. And these are important because neither the UV nor the near infrared affects the appearance of a surface. It's only the visible light. That's why we call it visible. We can leverage this by designing surfaces that reflect sunlight as needed to give you a particular color, but reflect as much of this longer wavelength near infrared solar radiation as possible. Now here's an example in panel B of a pair of brown surfaces. There's a cool brown and there's a standard brown. They look pretty much the same, and you can tell when you make measurements, either by just using your eye or by noticing that the reflectance versus wavelength in the visible part of the solar spectrum overlaps very well. But once you move into these longer near infrared wavelengths, the two curves diverge, and we can observe that the cool brown is reflecting much more strongly this invisible part of the radiation. And the end result is that the cool brown will reflect about 25% of the sunlight, while that standard brown in this particular example is reflecting only 8%. In panel C, we show some examples generated by a company that makes cool colored coatings for tile products. And we can note that even for a black surface, as shown at the left, you can attain a solar reflectance exceeding 40%. And that's because this black was designed to reflect as much of that near infrared radiation as possible. So bottom line is that cool surfaces can be white, but they can also be non-white. Now, before anybody panics about the small type in this, I'm going to blow it up in just a moment. But I'd like to talk about when do you want to go cool with your surface. And I would say that the most cost-effective and green path is to choose a cool roof product for new construction or when your roof needs to be replaced at the end of its service life. And that's because if you have a brand new roof and you decide to tear it off for the purpose of installing a more reflective roof, that's a big waste of money and embedded carbon, and it's not going to pay for itself. But if you choose a cool roof when you are first constructing the building, well, that cost premium is often about zero. And if you choose a cool roof when you have to replace the roof because it's reached the end of its service life, which is typically about every 20 years, again, the cost premium is often about zero. So that's the way to do it. Now, for those who can't read extremely small text, here's a little zoom into just one example. I'd mentioned that white roofs are getting to be an increasingly common option for some buildings in the United States. And if you have a building with a large flat roof, the white surface is often provided as a single ply membrane. Well, if you had a black version of a single ply membrane, it would reflect about 5% of the sunlight. If you have a cool version of a single ply membrane, which is typically a bright white, well, that's going to reflect about 70 to 80% of the sunlight. What's the difference in cost between the two? Zero. So that's just a no-brainer. You get to get a light-colored surface, and you've got it for the next 20 years or so. And for some information about the different sorts of options and what their reflectances can be and what costs you might expect, I recommend visiting the Cool Roof Toolkit provided by the Global Cool Cities Alliance. That was roofs. Let's talk walls. Cool wall products that have high solar reflectance, or albedo. Albedo and solar reflectance are just two terms for the same thing. They're sold today, most aren't yet marketed as such. In this picture here, I'm showing a variety of commercially available wall products, mostly exterior wall paints. And they come in dark colors, they come in light colors, some have a high solar reflectance, some have a low solar reflectance. But in my worldview, what I would say is that if you have a wall that's reflecting somewhere between 40 and 60% of the sunlight, and that doesn't have to be a very light color, I'd call that a lower tier cool wall. And then if you have a wall that's reflecting at least 60% of the sunlight, that's a higher tier cool wall. to me. And those are available in a variety of colors. Some are off-whites or dull whites, like we see up on the top. And that's just common. Just walk around, you'll see walls that are done like that. And others will be using special cool formulations of wall paints, and they'll have a wider color range. If you'd like to learn more about the benefits and choices for cool walls, I put a link in here to a report that we did following a 3-year study of cool wall technologies and benefits. Moving down a little bit, we started at the roof, we migrated to the wall, and now we're reaching the ground. Let's think about what you can do for paved surfaces. Well, cement concrete pavement, that can be reflective. Or if you are starting with an asphalt concrete pavement, it's hard to make asphalt concrete by itself reflective because the asphaltic or bituminous binder is very dark, but you can apply a light colored coating or a cool colored coating and make it reflective. So here are some examples. We have workers applying a white coating to an asphalt concrete street. We have one of our former students at Berkeley Lab was measuring the reflectance of a variety of cool colored coatings that were produced by another company. You can make lots of very pretty pavements if you use cool color coatings. Of course, there are ordinary technologies available, such as white pavers. If you have an ordinary cement concrete sidewalk, as shown just beyond this sort of yellow border, kind of nice looking here, you can see that it is inherently lighter in color, and it also happens to be more solar reflective than this freshly paved asphalt concrete street next to it. So thanks. So just to switch to cement concrete can help. And as our previous speaker mentioned, probably a better way to get a more reflective and less carbon intense concrete pavement is to use slag or fly ash is another possibility, or other supplementary cementitious materials in place of cement when you're making your concrete. Now, those are some of your options. Now, where do you want to do this? Bottom line is that cool roofs and cool walls will save energy and carbon across California, across the southern half of the United States. That'd be climate zones 1 through 4 for people to think about that way, and beyond. Roofs are good also in climate zone 5. Now that's energy and carbon emission reductions. Reflective surfaces will also provide global cooling anywhere, although the exact magnitude varies, as mentioned before. If you want to see more about these savings, I've got a link in the lower left corner. If you want to find out what kind of savings are available to you for energy, emission, and cost, well, I recommend that you download our Cool Surface Savings Explorer. In this, you can enter your location, your type of building, the vintage of your building. I mean, is it new or old? What surfaces you plan to modify, the roof, just one wall, a couple of walls, all walls, how reflective that new surface would be. Are you using a white or a cool color? And then you can tell it, do you want to learn more about your energy cost or your site energy or source energy or carbon, or a bunch of choices there. And then you can decide, do you want to get the whole building savings or the savings per unit wall or roof area? All these choices, just pull down menus in an Excel tool and it will give you your results. So if you'd like to obtain this tool, I've given you a link here. You can go ahead and download the Cool Wall Application Guidelines, which include a link to getting this tool, which covers both roofs and walls. Where do you get products? Well, for roofs, it's now a no-brainer. Visit the website of the Cool Roof Rating Council, where they provide roof product ratings, incentives, and other resources. The rated products directory for roofs includes over 3,000 products. It's up to date. You can get information about the initial and aged radiative properties. There are, in some cases, I believe, links to manufacturers, or there will be links to manufacturers. The Cool Roof Rating Council's website also provides lots of helpful resources to understand what cool roofs can do for you. So there's some links down here. I'm excited to share that the Cool Roof Rating Council has this year launched its wall rating program, and that wall product ratings will go live soon. So visit them to see more about the wall rating program, but this will, I think, help you choose cool wall materials once you can find product ratings. For pavements, the Global Cool Cities Alliance, through its Cool Roadways partnership, has compiled lists of cool pavement coatings from over 10 suppliers. And that will give you some good leads on where to find cool coatings for our streets. There's a link down there which will take you to the list of information from the manufacturers. Now, researchers are continuing to develop exciting new cool surface materials.
1 minute left.
There are many from workers around the world. I'll just tell you about 2 of them. One comes out of some colleagues of mine at Berkeley Lab who've developed a temperature adaptive radiative coating. It's really a film that reflects 75% of the sunlight. But the clever part is that it radiates heat when warm. It has a high thermal emittance for those in the know. But it retains heat when cool. The thermal emittance goes low when the surface is not so warm. So that's helpful in summer and in winter. And this material has a high solar reflectance all the time, so it's always going to provide that global cooling benefit. Another is from our colleagues at 3M. They've developed a passive radiative cooling film that has a very high solar reflectance, 93%, and at the same time also has a high thermal emittance, just shy of 90%. And this is in a thin polymer film that can be applied with adhesive to an existing surface. So that's a very helpful retrofit option for a variety of different surfaces, and the links are below. Finally, for those who want to learn lots more about the cool surface choices, I recommend visiting the websites of the Global Cool Cities Alliance, where they look at the big picture very, very well, all sorts of aspects, from energy to health to the power grid to making good jobs. Cool Roof Rating Council, for the reasons I mentioned before. If you want to find cool roof and very soon cool wall products, that is your go-to destination. And we can't forget our friends at the U.S. Environmental Protection Agency, because for a long time now, they're providing the public with a tremendous amount of helpful information about how cool surfaces and other strategies such as urban vegetation can be used to mitigate the urban heat island effect. And with that, I think my time is up. So thank you very much for the chance to speak to you. And here is my contact information.
All right. Thank you, Dr. Levinson. We got a couple of specific questions here on your presentation. Is the cool surface calculator tool only for cool walls?
No, it is for both cool walls and cool roofs.
And we also got the question, is anyone compiling ratings for cool pavements? If no, how far out do you think we are from having that available?
Well, interestingly, I can say that this is a topic of discussion at the Cool Roof Rating Council. It's very early days. I think sooner or later there will be ratings available for pavements. It's just not something that's going to happen next week.
Okay, great. All right, I'm going to move on to bigger questions that could that might address any of the presentations. Let's see. One is Hashem Akbari mentioned that the IPCC had established a CO2e for albedo. Have any countries, states, or carbon registries started to factor this into their climate change mitigation pathways?
The short answer to that question is I am not fully aware of the international efforts, but I know that in Europe, countries have been considering that. And besides that, the response to global warming and CO2 emission controls have not been very aggressive over time, and there had been one step forward, two step backward, as you see in many policies around the world. And knowing that we have a portfolio of responses to global warming and climate change, the focus of each country is different, but currently most of the focus is in the introducing limits to CO2 emissions, and in terms of the energy efficiency, and in terms of the direct effect of the reflectance on global cooling, there is still a big debate, and many countries are not in that direction.
Is there anyone else in the group who wants to comment on that before I move on to the next question? Okay. Which carbon registry is the most advanced in establishing a methodology for carbon credit generation using man-made albedo activities?
Let me just say that comparing them would be difficult, and one has to evaluate 2 or 3 major carbon registry and coming up with a specific recommendation for their area of interest.
How can someone such as a city planner measure the albedo of existing surfaces, roofs, walls, pavements, to contribute to an evaluation of the best use of a budget for albedo management?
I'll take that one. So the tools that are used to measure albedo are not the kind of thing that are as common as, I don't know, phone cameras or something like that. So you really need to have someone who has the right equipment for this. There are test laboratories that are accredited with the Cool Roof Rating Council that can go make such measurements. So if you are a city person, you probably want to hire one of those labs or get an academic involved. If you're really interested, talk to me and I can tell you how you get the right equipment, but it's just not the kind of thing that you're going to have in your garage. Or another way to do that is if you know what sort of material is on your roof, there may already be a rating for it, and you could find out from the rated products directory.
So Ronen and Maria, to what extent could it be done with remote sensing, just using the photos on Google Maps?
I can take that, or Maria, you can take that.
I have no knowledge on how to do that with Google Maps, but of course, satellite instruments exist that measure exactly the reflection of sunlight. I guess for being able to map an area of a city, it would have to be highly resolved remote sensing data. So I guess geostationary satellites could be helpful there.
Do they exist? Do you think there might be data sets that would work?
I think so. Yes, definitely. I know for sure that EUMETSAT puts out solar radiation data at relatively high resolution.
So my colleagues and I have worked on this in the past. And the answer is that, yes, you can do this to some extent using what are called hyperspectral cameras on satellites, those that just look at a wide range of radiation. And you can also do this by leveraging some images that are taken by, of all organizations, the US Department of Agriculture. They fly planes that have cameras that are meant to detect vegetation. And we've done work before to relate those 4-band images, blue, green, red, and near infrared, to albedo. So these things can be sensed remotely, and I know that there's some proposed work now to try to do a more accurate job of establishing what is the albedo of the world as it is today from remotely sensed images.
I also would like to add 2 caveats to the limitations of the remote sensing. The remote sensings per se only measure the incoming radiation to their sensors from the either reflected or emitted sources. So all the satellite-based imageries are assuming certain emissivity in order to calculate the surface temperature. So a metallic surface with a low emissivity that can be awfully hot on a satellite imagery would show as a cool surface. So there are general ways of using this data, but one does not really have to worry about much about the existing setting. As Ronan was saying, when the time comes in for the replacement, either a surface or a roof, using the coolest technology at the time. So by that way, you can develop good policies toward advancing and changing the society within a short period of 20 years. Pavements need to be resurfaced between 7 to 15 years. So you can basically do all the pavements within 20 years. And the same story it goes with the roofs. If you have a good aggressive programs in place, you can make your cities cool within about 20 years.
Okay, we've got a little collection of questions relating to cool pavement here. How much is the savings from cool pavements reduced because the cement in concrete roads is a big CO2 contributor?
Hissam, do you want to take that, or should I take that?
I can take that. You can, well,
go for it.
On top of that, if I miss any point, I'd appreciate it. Like I discussed briefly at the end of my presentation, there are multiple choices to make the pavements more reflective. One of these solutions are using concrete pavements or concrete sidewalks in general because of the inherent lighter color of the pavements. And when we think about it, we should probably think a little bit broader, because the implication of pavement material choice is not only limited to the albedo and the embodied impact associated with the materials production. Lots of research studies have shown that there is an interaction between the vehicle fuel consumption and the pavement choice. And we can see how pavements can affect the excess fuel consumptions induced by the surface roughness or the properties of the pavements. So we think about this as one part albedo benefits, one part embodied impacts, and there's another part of this puzzle, which is the fleet transportation GHG emissions that is attributed to the pavement properties. In addition, you probably have seen all these efforts and claims by different industries, including cement and concrete industry, to achieve carbon neutrality by a certain period of time. And there are some efforts to use, for example, these byproducts from other industries, or even using natural products like limestone powder as a replacement of Portland cement to reduce the GHG emissions. So these are some of the alternatives. First, it is important to consider the whole context, including the transportation GHG emissions, pavement materials, and also maintenance and repair, as well as the albedo effect. Second is to consider decarbonization solutions even for the materials, even we are choosing asphalt or concrete or reflective concrete or reflective asphalt. Hope that helps. Ronan, please.
Yeah, so I'll just add to that. We did, in conjunction with the University of California at Davis and a number of other parties, an examination of the life cycle energy and carbon consequences of reflective pavement solutions. And what I'll say is that the bottom line is for cement concrete pavement, you got to get the cement out. Cement is just hugely energy intensive. So if you're going to replace it with what are called supplementary cementitious materials, such as slag or fly ash, then that's a big win. You, of course, need a supply of that stuff, and that can be a bit of a challenge in some cases as heavy industry has moved. But those will give you highly reflective concrete pavements, and they are essentially treated as having no embedded carbon because they're regarded as waste products. But if you are using traditional cement, it's just very energy intensive. So you're not going to win in an embodied carbon budget using traditional cement. That's my take on after our multi-year study.
Okay, continuing on the concrete and cement questions, the pavement questions. Are there any safety considerations for glare reflectance from cool roadways?
Again, Hassam, do you want to talk about this, or should I talk about this?
Sure, I can make a point and please follow up. It's a good question, and it's usually asked when we talk about reflective pavement because it's at the lower surface level and people are walking in that surrounding neighborhood. And I would usually discuss with my audience is that it's exactly analogous to surrounding buildings and adjacent building to that pavements. So if you make the buildings hotter than a usual amount, you probably have difficulties with the people in that neighborhood and citizens as well. However, there are two important aspects here. One that I discussed, one is about the context. There are multiple studies, for example, in Middle East, in Europe, that considers the thermal comfort of the residents when they make the pavements more reflective. These are experimental studies, and they found that increasing the pavement albedo would give benefit to the residents in terms of the thermal comfort because of the locations and because of the mitigation in the urban heat island intensity. So this is one factor. For example, in very condensed, densely built neighborhood, they saw that urban heat island effect is the dominating factor than the incoming solar radiation or incident radiation. Therefore, using cool pavements can mitigate the urban heat island effect, therefore an improvement in the thermal comfort of the citizens. While in a sparsely built neighborhood, because we have a large amount of incoming solar radiation to the pavements, going above the albedo of 0.4, 0.5 would cause thermal comfort issues. This is the study that I'm talking about, was conducted in Japan. That was my experiences on that.
All right. Well, I think the original question was about safety considerations for glare, right?
That is correct.
And so to talk about that, let me give you some context. The kind of albedo increases that Hassam was talking about in his presentation, a boost of 0.2, that's pretty much what you get from going from a new-ish asphalt concrete road to your typical sidewalk. Your typical sidewalk is made of gray cement concrete. I've never experienced a glare concern from an ordinary sidewalk. Mm-hmm. If you want to understand how really not bright that cooler pavement is, if you were to look at a median divider on a highway, you'll see those are often bright white, either painted white or made with white cement concrete. Those are like 70% reflective, way, way higher than anything that is being proposed right now. Mm-hmm. And I would be shocked given the difficulty of trying to keep anything really white. I mean, roads are a tough surface for that. I don't think we're ever going to be dealing with solar reflectances above about 0.4 for roads. So glare won't be an issue. And if you go to some parts of the country, my folks have retired to Florida, as is everybody else in New York, you will see light-colored roads because they're working with light-colored aggregate. In fact, their bigger challenge there is to make the striping visible, so they have alternating black and white stripes. All right, so that's not glare.
Let me just add on to a couple of examples to what Ronan mentioned, and with a little bit of definition. Glare is basically related to a specular reflection of the sunlight. Most of the urban surfaces would reflect in diffuse form, so they would not produce glare within a reasonable range. So on every day that we drive, we pass patches of freeway that are concrete, and they are distinctly higher solar reflectance than the asphalt concrete that is surrounding it. And nobody would be worrying about glare. At the same thing, as Ronan mentioned in his presentation, there are so many white walls, light color walls with a higher, more reflectance than the pavements, and that does not producing any glare. So the issue of the glare is only an issue if you are going to high, very, very high solar reflectance in excess of 0.6, 0.7. And here we are talking about a nominal increase in solar reflectance of going from 0.1 to 0.3. So glare is a non-issue.
Okay, one more question on road surfaces. It's actually a pair of questions closely related. What are the maintenance implications of asphalt surface treatments? There's a hesitation out there on the longevity of these coatings. And then the related question, the benefits of cool paving coatings, unlike roofs and walls, which we do not walk on, seem to be great at a faster rate. It seems that the replacement cost should be taken into consideration.
Yeah. Again, I can talk about this, but I'd give the other panelists a chance to weigh in.
Go ahead, Ronan.
All right, sure. So can I have the first question again, please?
What are the maintenance implications of asphalt surface treatments? There's a hesitation out there on the longevity of these coatings.
Sure, and frankly, these all need to be tested, and cities such as LA and Phoenix do have demonstration programs in place. Longevity can be thought of as either staying reflective or not peeling off or otherwise failing. So there's a challenge for staying reflective for any kind of road surface because tires deposit rubber, carbon, oil, all sorts of good stuff, or bad stuff really, on the roads. So you need to find a surface that will not soil so badly. Then there's the mechanical durability. And I can't really speak to that, except I could mention that the road surfaces get refinished pretty regularly anyway, whether you have applied a cool coating to it or a more traditional asphaltic slurry seal coating. But for walls and roofs, we sort of rely on the manufacturers to ensure that they are providing a durable product. The same thing really is true when it comes to paved surfaces. We have to rely on the manufacturers to deliver something that isn't just reflective, but will work over whatever its service life is supposed to be. What was the second question?
The benefits of cool paving coatings, unlike roofs and walls, which we do not walk on, seems to degrade at a faster rate.
Yeah.
Shouldn't we be concerned about replacement cost?
Yeah, and it's a reasonable concern. Of course, pavements do get serviced regularly, no matter what kind of pavement they are. But I definitely agree that we have to make sure that whatever we are using is not going to have a substantially shorter service life or otherwise not work out. So testing is underway.
I would like to add a couple of observations to that. A dark surface after aging is still going to be dark. An asphalt, when you install it initially, has a reflectance of about 5%. Depending on the type of aggregate that you have, its age reflectivity may increase to 0.1 to 0.12. A concrete paver that it is being installed may initially have a solar reflectance of 0.3, but over time it would age to a lower value. So any observant would still see that a aged concrete is still lighter than an aged asphalt. Having said that, we are a lot more advanced in terms of measuring the age reflectance and aging of the roofing and the wall materials. And as Ronan mentioned, we need to make significant advances in that area for pavements.
Okay,
Maybe one
so
sorry, I just want to add 2 points quickly to this topic. When we make a decision to make the pavements reflective, 2 parameters are very important here. One is the traffic level. In highways, in high volume traffic roads, more than 70K vehicles a day, that wear and tear is very significant, that almost probably no reflective coating can overcome this issue, and keeping the albedo value high is difficult. And the second part is, as the other panelists mentioned, about the durability factor of this pavement against weathering issues and the durability against the local temperature. To what extent we want to maintain the albedo, and what are the common practices, the historical practices in different case studies, including pilot projects.
okay, so I'm getting signals from the event organizers that we're already half an hour past our time on stage. So there's several interesting questions remaining. Climate Resolve will be outputting a white paper related to this event in the future, and in a moment you're going to hear a couple words from Seth Jacobson about that. And so I'm going to close out the panel portion, but after Seth has given his closing comments, all of you, and I mean you as in the audience listening, you all will all find yourselves deposited back into the conference area, and you will be able to find the speakers there as well, just among the rest of you. And you can find, if you sit at their table, you'll be able to ask your question there if we didn't manage to get around to it here on stage. So so thanks to all 4 of you for taking your time to enlighten us all about albedo and its relationship to climate management. And I'm going to hand the reins over to Seth from Climate Resolve. So thanks again.
Thank you, Roel, for leading that insightful discussion. I'm Seth Jacobson, and I'm Managing Director of Solution Services at Climate Resolve. We want to thank all of our panelists for sharing their essential research with us today. We recorded their presentations, as Roel mentioned, and will notify all registered attendees by email when we post the video online. In addition, our team plans to work with Roel, as he mentioned, and the panelists to synthesize their presentations and discussions into a white paper and we'll notify you when we've posted it. Finally, we again wish to thank our sponsors Climeco, Skanska, Latham & Watkins, GAF, and the Adrian Arsht Rockefeller Foundation Resilience Center for their generous support that made this event possible. We're now going to invite all of you to enjoy our networking event. Attendees registered for this event from industry, policymaking, and other stakeholder groups. And our panelists, as Rule mentioned, will be sitting at the virtual tables to continue the discussion with you. Our networking event will be open until 1:30 p.m. Pacific time. Thank you again from Climate Resolve.